today is okay. So today the session is will be devoted to questions and answers related with my first two lectures. Okay, during a couple of weeks ago, I was delivering a lecture on the basic meaning of the Schrödinger equation, and last week I was solving this one particle like a Schrödinger equation in three very simple problems. So one of them was the free electron gas, the other was the hydrogen atom, and finally I was discussing the harmonic oscillator. So I was asking you to pose any questions beforehand in order to prepare some extra slides or some extra material to clarify some concepts or the meaning of some issues that appeared in the lectures. I've got just one question, okay? So I will start with it. So the question is by Bummi Jacob Akeredolu, and the question is, you explained that the square of the wave function represents the probability density, which gives the likelihood of finding a particle in a given system relative to its position, momentum, energy, etc. So my question is, what is the physical significance or implications of the wave function itself? Okay, so that's the question. The question is, what is the physical meaning of the wave function? And more than the square of the wave function. Okay, so I have prepared here a few slides to answer the question. So these are at the very end of the first lecture, so I will deliver again the slides after the presentation today. So if you remember a couple of weeks ago, I was ending my presentation with the principles of the Copenhagen interpretation, and that was the last slide. So I have prepared here some extra material that is related with the physical meaning of the wave function itself. Okay, so in quantum mechanics, the wave function is a very fundamental entity because it contains all the information about the quantum system. If you know the wave function of a system, then you know everything about that system. And in particular, if you know the wave function of a system, then you can apply the corresponding quantum operator related with a given observable, for instance, the position, the momentum, the Hamiltonian, the angular momentum, whatever observable that you want to measure, then it will have the corresponding quantum mechanical operator associated to it. And then if you know the wave function, the thing that you can do immediately is that you can extract the expectation value and the different probabilities of getting different outcomes from measurements. So that's the first very important property of the wave function. So you know the wave function, then immediately you have access to expectation values and probabilities of finding a given output of a measurement of whatever observable. So that's the first thing to say. But there are other properties related with the physical meaning of the wave function. So the second thing that is very important is that if you take a look to the Schrödinger equation, you can check how the Schrödinger equation is linear. It's linear and homogeneous, okay? And that means that if you have two solutions of the wave function, then you can superpose them linearly. You can make a linear combination of those solutions. And that means that the wave functions allows for this quantum superposition. And that means that a given system can exist in multiple states simultaneously until they are measured. And this leads to very important physical consequences like the interference in phenomena like the double slit measurement. So that's the second thing that is related with the property that the Schrödinger equation is linear. And therefore, the solutions can be linearly superposed. So the third thing is that the wave functions do have a phase. And in principle, the wave functions are complex numbers, and therefore they have a phase that is associated to the given complex number. And this phase plays a very important role in quantum interference. In particular, if you have two different wave functions, then the relative phases can change when they combine, and they can give rise to constructive or destructive interference. So that's another property of the wave functions. Then one thing that is also very important is that we can follow deterministically the evolution of the wave function. And in particular, if you know the wave function of a system at a given time, then you can evolve deterministically the behavior of the wave function and the evolution of the wave function just solving the time-dependent Schrödinger equation. So the time-dependent Schrödinger equation is giving you how the wave function is changing as a function of time. If you remember, you had the imaginary unit, then h bar, and then the time derivative of the wave function. And this was equal to applying the Hamiltonian operator to the wave function. Okay, so we can just we can ascertain the evolution of the wave function itself by using the Schrödinger equation, the time-dependent Schrödinger equation. Then another thing that can be explained from the knowledge of the wave function is that you can expand your wave function as a linear combination of eigenstates of eigenfunctions of a given observable. And the coefficients of this expansion can give you the likelihood of getting the corresponding eigenvalue in a measurement. So before the measurement, in particular, this probability, this likelihood to get a particular eigenvalue as a result of a measurement is related with the square of those coefficients. So before doing a measurement, then this expansion is giving you the probability of getting different numbers in the measurement. And then if you perform a measurement, then what is called the collapse of the wave function will be produced. And that's that after the measurement, the wave function will change to the corresponding eigenfunction or the value that has been measured. And this is called the quantum collapse. Okay, and this leads to the probabilistic nature of quantum mechanics. So that's as a summary. While the wave function itself is not directly an observable, it is a very important mathematical and conceptual tool for understanding quantum phenomena. And essentially, the Copenhagen interpretation is giving us just it's presenting it as a tool for predicting the measurements outcomes of a given observable. So that's a summary of the answer regarding what is the physical meaning of the wave function itself, not only the physical meaning of the square of the wave function. So I don't know if this answers the question posed. So Bumi,
Yes, you've done justice to the question. Thank you very much.
you are
I'm
very
welcome. Glad. Yes, thank you.
So I will share the slides again with this extra documentation at the end of the session today. I will circulate it. Are there other questions? Because I haven't got any extra email, and I don't know you have. questions regarding the first two lectures, regarding the meaning of the Schrödinger equation or the solution for these very simple cases. Again, I mean, I'm not asking you just for questions that are very, very related with your topic of research that can be covered in further lectures or even directly during the ASESMA school. So here is I'm intending to answer your question related with the lectures that I was delivering.
Hello.
Hello.
Yeah, so thank you. I want to ask a question on um, modeling realistic potentials, for example, of a molecule or a crystal. Can you just speak to how to model, I mean, realistic potentials?
Yes, sure. So thank you for your question. So this is um, a very important question, and it is very pertinent. So during the second lecture, I was giving you the shape of very simple potentials to start with. So the first potential is trivial. The potential was zero everywhere. Okay, so it's absolutely constant. So then we could introduce the meaning of a plane wave as the solution of this um, free particle-like system, and we were ending with the solution of a traveling plane wave. Then I was introducing a little bit more complex potential that was the Coulomb potential, 1 over R. And then we were solving the hydrogen atom. And then finally, the harmonic potential that goes with the position square. And then we had this. So what does happen if you have a molecule or if you have a solid or whatever? Then the thing is as follows. The system that you want to study is an electronic system. And in this electronic system, then within DFT, the thing is that you are going to map the problem of interacting particles. That is a problem that is very difficult to solve, if not impossible, beyond a few electrons. Then you want to map this very complicated problem in a problem of independent electrons. Independent electrons that are just moving in a potential that is generated by the nuclei and an effective potential generated by the rest of the electrons. Okay, so how to introduce this potential in the one particle quantum equation that is essentially is very, very similar to the one particle Schrödinger equation. So for the nuclei, what we are going to do is that you are assuming, or you will assume, that the nuclei are very heavy objects. The mass of a nucleus is much, much larger than the mass of the electrons. Okay, so let me check if I have some slides here that I can share with you on this topic. Mm. Yes, so I have it here. So I will share this with you and then we can start the discussion from this. Okay, so. Okay. So imagine that you have a molecule and or a solid or a condensed system. Okay, and then we are going to work within DFT. So within DFT, what we are going to do is to map our system of interacting particles, in particular interacting electrons, on an auxiliary problem where we are going to deal with an independent electron that is moving in an effective potential generated by the rest of the electrons. And then here, to do this, we are going to resort to a different approximations. So the first approximation is the Bohr-Oppenheimer approximation. Okay, so the Bohr-Oppenheimer is based on the fact that the mass of the nuclei is much larger than the mass of the electron. Sorry. In particular, one proton has, roughly speaking, 2,000 times more mass than one electron. So this ratio is the same ratio that between a newborn baby and an adult elephant. Okay, so if one newborn baby is an electron, then one adult elephant is one proton. And in a nuclei, typically you have more than one proton. Okay, for in silicon, you have 14 protons and very likely of the order of 14 neutrons. So you have, roughly speaking, the ratio between the mass of an electron and the mass of a silicon nuclei is the same ratio between one newborn baby and 28 adult elephants. So this translates into the fact that the velocity of the electrons, since the electrons are much lighter than the nuclei, then the velocity of the electrons is much larger than the velocity of the nuclei. Typically, just to put some numbers here, the velocity of the electrons is of the order of 10 to the 8 centimeters per second, while the velocity of the nucleus is, roughly speaking, the velocity of the speed of sound, and this of the order of 10 to the 5 centimeter per second. Okay, so we can see how the electrons are moving 3 orders of magnitude faster than the nuclei. So if one nuclei moves 1 meter, then the electron in the same amount of time will move of the order of 1 kilometer. So that means that we can consider that at any moment, the electrons will be in their ground state. So they move so quickly that if the nuclei move behind, the electrons will accommodate to the ground state very quick. Okay, and then we can assume that the electrons will be in their ground state for an instantaneous ionic configuration. And this helps me to simplify the problem. And in particular, instead of having a problem when we have nuclei that here are represented by these blue balls with an arrow, the nuclei are moving, and electrons that they are represented here by a red ball just moving also with following the direction of the arrow, then first we can assume that the nuclei are fixed. And that means here that we can assume that the positions of the nuclei are just fixed at a given time, and then solve the electronic equations, assuming that the nuclei, are fixed at those particular positions. And then once we have the solution for the electronic problem, then we can move the nuclei as classical particles in the potential that has been generated by the electrons. So the electrons in the ground state, they will have a charge density, and then we can compute the potential that the electrons are acting on the nuclei, and then we can move the nuclei, assuming that they are classical particles. And we can assume that they are classical particles in most cases because they are very heavy. Okay, as usual, every single approximation do have their own limitations. Okay, so there are some cases where we have to consider the movement of the nuclei in a quantum way, or whether we cannot assume this Bohr-Oppenheimer approximation. But this is basically the Bohr-Oppenheimer approximation. So this allows me to simplify my Hamiltonian. Okay, so here I have the Hamiltonian of my system. So the Hamiltonian is related with the energy. It's the operator related with the energy. So my system of nuclei and electrons in interaction has a different contribution to the energy. So here we have the kinetic contribution to the energy due to the electrons. We have the contribution to the energy coming from the kinetic energy term from the nuclei. Then the electrons are interacting between themselves, and therefore we have this repulsive potential between them. Then we have the Coulomb attraction between the electrons and the nuclei, and then we have the repulsion between the nuclei between themselves. But using this approximation, I mean, using the approximation that the nuclei are fixed, the atoms are fixed, then they don't have kinetic energy, so we can just skip this term here, because if they are fixed, the kinetic energy is 0. Then, since the positions are fixed, this term here is a constant, because the atomic number of the nuclei are just a constant, and the positions of the nuclei are also constant. So everything here in this term is a constant. So that means that this is just a scalar. And then we have this term here that is a fixed potential that is external to the electrons. So the system that we will be interested in is a system of electrons. And therefore, the potential generated by the nuclei is external to the system of electrons, okay? And this potential here, since the positions of the atoms are fixed in this approximation, and the atomic number is also a constant, then this is a fixed potential external to the electronic system, okay? And then finally, we have this term here that is related with the electron-electron approximation. So as you see, we have decoupled my problem in using this Bohr-Oppenheimer approximation. We have decoupled my problem in an electronic problem where the Hamiltonian is like this: the kinetic energy of the electrons, the electron-electron interaction, and this external potential generated by the nuclei on the electronic system. And then we want to solve this Schrödinger equation for my electronic system, okay? And once this electronic problem will be solved, then we can go and solve the problem for the nuclei, okay? So we can move, we can compute the force that the electrons are exerting on the nuclei, and then we can solve the equations of motion for the nuclei, typically in a classical framework. So as you see here, we have a first approximation for our Hamiltonian. Then, still, this problem here is very complex. Okay, this is not just to solve this problem. This is not trivial at all. So here we will have different approximations. Some of them are directly related with some topics that will be covered in the ASESMA school. For instance, this external potential related with the interaction between the electrons and the nuclei. Then, as you will see in the ASESMA school, we are going to deal with some pseudo-potentials. In particular, we are going to assume that not all the electrons will play the same role in the chemical bonding. In particular, there are electrons that are very, very tight to the nuclei. They don't interact at all with the rest of the electrons, and the only role that they will play is just to screen the potential generated by the nuclei. So the thing that we are going to do is to replace the potential generated by the bare core and the core electrons by a pseudo potential. And then there will be an extra approximation on this term here. And finally, we have this term here that is the term that complicates the problem deeply. That is the electron-electron interaction. And for this, the thing that we are going to do is to use DFT. And with DFT, we are going to approximate somehow this electron-electron interaction by potential and by a functional of the density. Okay, and there are different approximations, different flavors for this functional and for this exchange and correlation potential. Okay, so those questions regarding the exchange and correlation potential that somehow models this electron-electron interaction, and the pseudo potential that models also this electron nuclei interaction will be covered in the ASESMA school. And that's essentially, or that's the way how we can approximate a Hamiltonian in a typical molecule or solid. Okay. In summary, just to put, just to take here a take-home message. If you have a molecule or a solid, how the Hamiltonian would look like. So we will have here a term that is related with the kinetic energy of the electrons. Then the atoms will be located at some fixed positions in space, and we are going to put a pseudo potential at that particular position. And then for the electron-electron interaction, we are going to use a given exchange and correlation potential. And with these three terms, then you have the Hamiltonian, and that's the Hamiltonian that we are going to solve. There's these different terms, the exchange and correlation potential and the pseudo potential will be covered in the ASESMA school. Okay. So does it solve your question?
Thank you.
So let me know if you need some further clarification on them. So any other question?
Yes, Prof. Good day, and how are you?
Hello, David. Yeah.
Yes. Prof, my question is very simple. I think it may be related to what you were explaining. Can we really solve the Schrodinger equation with the exact for solving all the system? Or maybe I phrase it very well. Can we solve the Schrodinger equation exactly for all systems?
Well, that's another very interesting question. So just let me.
Oh, thank you.
Okay. Okay, so just solving if you want to couple or you want to solve the full Schrodinger equation, that means including all the terms here. All the terms that will be included here, that's a very, very complicated problem. And in particular, it will not have exact analytical solution beyond 3 bodies. Okay, so somehow this has a parallelism in classical mechanics. So you take just the problem of the 3-body problem in classical mechanics, the problem of the sun, the moon, and the earth, for instance, and then you have only three body terms, then you will not find any analytical solution for that problem. In particular, the problem is chaotic, in the sense that if you change slightly the initial conditions, then you integrate your equations of motions for a sufficiently long time, then the results will be very, very different. Okay, in this particular, that was classical mechanics. Here in quantum mechanics, then the exact Schrödinger equation cannot be solved analytically beyond the three-particle system. So this is a very, very complicated problem. Typically, there are two different approaches here. Okay, there are more than two, but for the many electron problems, so just to solve, imagine that we apply this Bohr-Oppenheimer approximation, and then we can decouple the equation into an equations for the electrons, and then once you have solved for the electronic problem, then you move to the nuclear problem. So for the electronic problem here, that is a very complex problem by itself, then you have different approaches to solve it. Typically, if you are coming from the quantum chemistry community, then you can start using the Hartree-Fock approximation that is relatively crude, where you can include exactly the exchange interaction between the electrons. So in the Hartree-Fock, what we are going to do is to represent the multi-electronic wave function, because the solution of this problem here, in principle, what you have here in the parentheses are all the positions of all the electrons in your system. Okay, so what you have here is a system of many electrons, and therefore you need a multi-electron wave function here. So in the Hartree-Fock approximation, typically we are going to represent this multi-electronic wave function in a Slater determinant way. So in a determinant, if you change the position of two rows or two columns, then you change the sign, and that means that you exactly take into account the exchange of the electrons, and the exchange energy is accurately computed. And then you can go and include more terms related with correlation, and that means that the movement or the behavior of two electrons are correlated. They depend one onto the other, using more than one Slater determinant. And that gives rise to what is called the configuration interactions and further approaches on that. So what is the problem here? The problem here is the computational cost. So computational cost in two senses. First, the wave function here depends on the positions of many, many electrons. Okay, and there is the computational wall here that is telling us that it is the computational burden to solve this problem increases exponentially with the number of electrons. If you take a look to the Nobel Prize lecture by John Poppel in 1998, so he was discussing if a wave function like this, a multi-electronic wave function, would have any kind of physical meaning beyond a few tens of electrons. And he was arguing that the physical entity would be so complex that it would be very difficult to ascribe any kind of meaning to that multi-particle, many-body wave function. Okay, so we have the computational wall because the computational cost to solve this using these Slater determinants and adding more and more Slater determinants for just to considering the correlation between the electrons in a more deep way makes the problem essentially unsolvable for a reasonable number of electrons in a realistic problem. Then there are other techniques that I am not an expert on, but there are techniques that try to find the solution for the many-body electronic wave function using quantum Monte Carlo methods. So essentially, they are going to play a little bit with the shape of the electronic multi-electronic wave function and try to find, using this quantum Monte Carlo method, the one that just minimizes the energy. And there are other techniques that I am not an expert in, like perturbation theory, that they use propagators and things like that. So those are the methods that I am aware of. But essentially, the most used methods and the most accurate methods are those methods based on quantum chemistry, in the sense that, in particular, in the configuration interactions, including many Slater determinants, and then, I mean, you can get very, very accurate energies, just touching what is called the holy grail in quantum mechanics, that is the precision of 1 kilocalories per mole. But the computational cost is extremely expensive. It's you have the exponential complexity wall. Okay, and then you have also other methods that are based on quantum Monte Carlo. There are many different groups all around the world just working on these quantum Monte Carlo methods. Okay, so using any of these two methods, then you can get very accurate results for the multi-electronic wave function here. Okay.
No, thank you so much, Prof.
Check. So I'm trying just to. Okay, so Peter has raised his hand. Peter? Okay. I've seen another question in the chat. So it's when carrying out a structural optimization, specifically VC relaxation, are we trying to find the equilibrium forces on the atoms by solving the Schrödinger equation while considering motion of the nuclei in a potential generated by the electrons, as you have just explained the Born-Oppenheimer approximation? So I don't know what do you mean by BC relaxation, but if you mean, for instance, conjugate gradient relaxation, the answer would be yes. Okay, so in a conjugate gradient relaxation, if we want just to perform a structural optimization, or in avoiding optimization, for instance, the thing that we are going to do is we assume a given positions of the nuclei, and then using the Born-Oppenheimer approximation, we are going to assume that the nuclei are fixed. Then we compute the ground state for the electronic system. From this ground state of the electronic system, we can compute the forces on the atoms. And the thing that we are going to do in the conjugate gradient, for instance, is to move the atoms according to the direction determined by the forces. The force is the gradient of the energy with respect to the position. Okay, and then if we move the atoms in the direction of the forces, then the energy will be lowered. And then using special techniques, using this approach, we can move the atoms in such a way that finally the forces on them will be zero. So that's regarding to the question by Manuel Kibalazzi, the answer is yes. I mean, in relaxation, at least using the conjugate gradient or the Brownian relaxation, then we are going to use the Born-Oppenheimer as I was explaining. So there is another question by Peter Banda that is saying, okay, in the Hamiltonian that we have considered, is it possible to have a term of the potential due to the magnetic effects? Okay, this is another very interesting question. The answer is yes. Okay, so here, I mean, if you have a magnetic system, then the number of electrons with a spin up will be different than the number of electrons with a spin down. In particular, the charge density of electrons with a spin up and with a spin down may be different, may not be the same. And therefore, there are extensions of the density functional potentials to account for this. So for instance, the typical extension beyond the local density approximation is the local spin density approximation, where you are considering not only the charge density, but you are considering the total charge density, but you are considering in the expansion the charge density with a spin up and the charge density with a spin down that may be different. So that's one of the things. And the other is that on top of that, you can have different interactions related with the interaction between the magnetic moments and an external magnetic potential, okay, or a magnetic field. So those terms, for instance, there are some groups that have implemented the Zeeman effects on the electronic structures. And finally, on some particular systems, you may have also spin orbit interactions. Okay, so in some systems, the electrons, the spin of the electrons do explicitly see the lattice that is behind. And those relationship between the spin and the lattice are considered using this spin orbit interaction. So those are also related with magnetism. Okay. So there is another question by Adewale. Adewale has raised his or her hand. I don't know if it's a he or a she.
Yeah, thank you, Prof.
Yeah.
Yeah, you talk about the Born-Oppenheimer approximation, that the mass of the nucleus is very large compared to that of the electron, which makes the velocity of the nucleus very small compared to that of the electron. And makes it easy to decouple the electron and the nucleus. But I just want to ask, in case of a system where we have a strong electron nuclear coupling, in the process of decoupling the electron and nucleus, does it affect the accuracy of the Born-Oppenheimer approximation? And if that happens, are there any other existing approximation that can be applied in
I can hear. I can hardly. Sorry. Well, I can not hear you properly because I would acknowledge if you can write your question in the chat because I cannot hear you properly.
Hello, can you hear me now, sir?
Oh, now much better.
Hello, sir, can you hear me? Hello, Prof.
Hello.
Hello, Prof, can you hear me?
Yeah. Now I can hear you much better than before.
Okay. So I was saying that you talk about Born-Oppenheimer approximation, where you said that the mass of the nucleus is very large compared to that of electron, which makes the velocity of the nucleus very small and makes it easier to decouple the electron and the nucleus. So I'm like, in the system where we have a strong electron nuclear coupling, is Born-Oppenheimer approximation still applicable? And if that is the case, does it affect his accuracy? And if it does, are there any other approximations that can be applied in such a situation?
Okay. So you are talking about the limits of applicability, essentially the limit
exactly
of the Born-Oppenheimer approximation.
Exactly.
Okay. So there are some limits of applicability in the sense that, for instance, imagine that you have a very light nuclei. Okay, imagine that you have systems where you have hydrogens that is relatively light or with respect to the electrons or other very light elements. In those systems, in some cases, you may be very, very careful about whether the Bohr-Oppenheimer approximation can be applied or not. Okay, there are other cases. For instance, imagine that you are talking about stopping power. The stopping power is that you have a nuclear reaction, and as a consequence of these nuclear reactions, there are some particles that are very, very energetic because the speed of those particles is very, very high after the nuclear reaction. And then you have to stop them, okay, because they may be very harmful for the environment. And then you have to design the container for these nuclear reactions and how to stop these very energetic particles. Typically, in the alpha particles. One alpha particle is the nucleus of a helium atom. And then they are coming out of the nuclear reaction with very, very high speeds. In those cases, there may be interactions between the very energetic particle with the electronic cloud, and then you have to consider the movement, or you have to consider both the movement of the electrons and the nuclei at the same foot. Okay, and then you have to perform different techniques. You have to use different techniques, like it might be Ehrenfest dynamics or things like this. Okay, so that's another limit of applicability. And then you are talking about the electron phonon coupling, for instance. Okay, so how the electronic system can change with the movement of the atom. So how the electrons can accommodate to the movement according to a normal mode, such as a phonon. So in these cases, there are some techniques that allow you to perform the calculations on or within the Bohr-Oppenheimer approximation. Okay, so
Okay.
I can recommend some there is some very nice reviews by Feliciano Giustino, who is one of the fathers of all these electron phonon coupling terms that show how it is possible. And indeed, even during the ASESMA school, there will be some, or there will be quite a lot of lectures regarding these electron phonon couplings.
Okay. Okay, thank you, Prof.
You're welcome. So any other question? More questions? If not, Nicola, do you want to mention something regarding the following lectures on this preschool? Because I don't know if the dates have been already confirmed or not.
Yeah, actually, I was hoping that Garo would be here because I don't think he has finally confirmed. So, so in principle, we should have one next week at the same time. So we're gonna start talking about solid state physics with George Magnali and Garo Ghebreyesus. So that's it. And the other thing maybe worth mentioning, remember that the deadline to apply for the ASESMA for the actual school is 23rd of March, 10 days from now. So yes. So is there any question regarding this or?
Well,
Okay.
if not, it has been my pleasure to be with you during the last 3 weeks.